Hey, so hi everyone, and welcome to this researcher engagement meeting. So today we will be talking about advancing wind engineering research and education through WEUQ. This meeting is organized by the SimCenter Working Group on Wind and Water Simulation. My name is Seymour Spence from the University of Michigan, and I will be hosting this meeting. So we had some great presentations lined up. The first will be from Dr. Zsarnoczay from the SimCenter NERI. Then we have Professor Goulet from Stanford and Professor Roach from Auburn University, who will be giving presentations. At the end of our presentations, we will have a panel and group discussion. So our objectives with this researcher engagement meeting is to provide an overview of the latest WEUQ capabilities for wind hazard and damage simulation, demonstrate the WEUQ CFD educational module, highlight how WEUQ can be used to support research, teaching, and community engagement, and gather community feedback and identify future development needs through our panel and wider community discussion at the end. So you are welcome to participate using the Q&A feature. We will be monitoring the Q&A throughout the meeting. I would like to invite the presenters, when not presenting, to go ahead and start answering any pertinent questions in the Q&A. You can also participate through submitting questions in the chat. However, I would like to highlight how we will be monitoring the Q&A more closely. At the end of the formal presentations, we will have a panel discussion and wider community discussion. There you can not only submit questions through the Q&A feature, you can also ask questions verbally. Our panel discussion will start by addressing questions that were previously submitted to the Q&A. I would just like to remind everyone you will be on mute until called upon. So before moving on, I would like to provide some information of how you can stay involved with the SimCenter. So please go ahead, check out the SimCenter webpage, and in particular the Join Community tab. There you can go ahead, you can subscribe to the newsletter if you are not already subscribed. There are discussions you can participate in, and you can see when our future researcher engagement meetings are planned. We have a number of these in the upcoming months. Upcoming events, our next researcher engagement meeting will actually be tomorrow, December 4th, and it will focus on enhanced capabilities of R2D for regional disaster risk analysis. There is still time to sign up, so if you're interested, please go ahead and register. I would also like to draw everyone's attention to the upcoming NERI Computational Symposium that will be taking place in May at UC Berkeley. This is continuing on from the successful computational symposiums that we have had in the previous years. So I think this is going to be a great opportunity to share. We are accepting abstracts through December 19. So if you're interested, please go ahead, submit an abstract. So without further ado, I'd like to concede the floor to our first presenter, who will be Adam Zsarnoczay from NERI SimCenter. So Adam, the floor is yours.
Thank you, Seymour. Let me share my screen. There you go. Confirm that everything looks okay.
Yes.
All right. So welcome, everyone. My name is Adam Zsarnoczay. I'm one of the associate directors at the SimCenter and the senior researcher at Stanford University. And I will talk about the features or capabilities that our simulation platform and desktop applications have for wind engineers. Before starting this, I would like to stop for a second and acknowledge that most, if not all, of these features were developed by a postdoc at the SimCenter who is Abiy Melaku. He spent 2 years with us, and he made great progress in making these tools more user-friendly and available to those who are already wind engineers or those who are aiming to become one. He's also a wind engineer. So thank you, Abi, for all the work that you put into these tools. Now, I will start with a broader context to show you where wind engineering is and where these tools are in our simulation platform, and then focus on a couple of different use cases that demonstrate how you can use these tools and what features are available for you if you are interested in wind engineering. SimCenter spent the last 9 years on developing a conceptual framework for probabilistic risk assessment that is regional in scope, but it includes local analysis pretty heavily, and we pay attention to how those local, so single building analysis, are supporting the regional scale studies. Wind engineering and the features that we will show today are mostly concerned with local problems in our tools, but I will show how they are connected to the regional ones also. So when it comes to this conceptual framework, what we are going to talk about most of the time today is how you can do a hazard description or characterization, then some kind of structural analysis, and in the end, we will also look into damage analysis a little bit. But I want you to understand that there's much more to the SimCenter platform. And if you are interested in these other parts, I encourage you to check out a publication that we had recently and also to talk to us to learn more. So having this conceptual framework is great, but I think one of the strengths of our simulation platform is that we implemented it in a backend and in several different front-end desktop applications. Our backend is what does the simulations. It's written in C++ and Python, and our front ends are making this accessible to users through graphical user interfaces. We have different front ends for different use cases, and they help you go through the process of running these simulations from the beginning where you just set up the application all the way through configuring the simulation, running the workflow, and then processing and reviewing the results. We provide different levels of complexity for users with different needs. Those who want a streamlined analysis, for example, students who are only getting familiar with wind engineering, have many automations available to them that make it very easy to get something running. But those who are more like graduate students who want to do research and want to develop new models can go a little deeper, get their hands dirty, and then bring their own models into the platform and make use of the flexibility of this whole architecture and see how their models compare with what was already available, and then make these new models available to the broader community. We have this complicated figure that I'm not going to go into the details of it, but you see that we have figured out how to help users with different needs, and we provide different ways to use our platform for each level. So if you read that publication that I linked earlier, then you will see how this translates into actual use cases, and you will see how it could work for your own research or practical work. Now, when it comes to our desktop applications, we have a different application for each different use case that we identified. I mentioned that earlier. What we will focus on today is VUQ, our wind engineering with uncertainty quantification application. I just show this slide to show you that we have other applications for other purposes. So if you are also interested in those kinds of problems, then I encourage you to check out those applications as well. Now, when it comes to VUQ, what we are doing with this is fourfold. First of all, we want to help people get familiar with and we would like to support the education of more wind engineers who are well versed in computational methods. And we envision a new generation of wind engineers who are just as familiar with experimental work as computational methods and use them as complementary tools, and they can get much more done by having these two at their disposal. Besides computational fluid dynamics based approaches, we also have a bunch of stochastic tools for wind generation and wind pressure generation. And we also support bringing your own experimental data into the tool and use that directly for the calculations. So this covers the wind hazard part. We also have a structural response part in this application. All of our applications give you workflows. So you can step through different modules to get a complicated calculation done with these applications. So the wind part gives you the wind loading, and then the structural response part allows you to model a structure and apply that wind loading on it, and then see what happens to the structure. We use OpenSeas here to model the structural behavior, so it's a finite element method, and we provide a number of different modules that help you create those models and bring existing models into the workflows. Uncertainty quantification is the third part that I wanted to talk about. We don't want these analyses to be just deterministic. We want to help you do probabilistic analysis, either just forward propagating uncertainty or doing more sophisticated things like sensitivity analysis or reliability analysis. All of these are built into the tool and facilitate those kinds of analysis and making them part of your research. Finally, our most ambitious goal with this is to help you create surrogate models. So once you set up these workflows, you should be able to generate surrogate models that reproduce the expensive calculations and make it much easier to apply the same kind of fidelity to your analysis with a fraction of the computational cost. So this is what VUQ does in a nutshell. And I would like to focus on 4 different use cases next to give you a bit more details about the kind of problems that we see people use VUQ for already. The first one is a relatively simple starting point where people do sensitivity analysis using existing results from aerodynamic databases, such as the database from the Tokyo Polytechnic University, where you can this is bundled with our tool, so you can automatically access those results and then apply uncertainty either on the wind speed or on the structural parameters, and then do a sensitivity analysis to see how that uncertainty translates into the variation in the results. We have examples for each of these use cases that I'm going to mention. So if you go to the VUQ documentation, you can look at those examples where we provide a detailed description and guidance on how to run these problems and what decisions we made when setting up these problems and how you can deviate, what other options you have if you want to run similar problems for your research. So sensitivity analysis is the first. The second one that I will talk a little bit more about is creating digital twins, either digital twins of wind tunnels or digital twins of buildings in the wild where you want to reproduce the wind field around existing structures. Let me go a little bit deeper into this. So a traditional digital wind, digital twin would reproduce the entire wind tunnel, but what we are doing here is a compact version that you can see in the bottom right, where we only start at after the wind field has been created in the wind tunnel, and we use boundary conditions that are sophisticated enough to reproduce that wind field properly, and this way we have a smaller domain to simulate in, and hopefully that means that the simulations will get more efficient. Here are the steps that we use to create these digital twins, and we provide you help and guidance through the desktop application to go through these steps and to make the right decisions. It is not completely automated. I have to give you that caveat. You have to know what you're doing. So this is I would say this is an educational tool. If you use it within the scope of a class, for example, where you are being taught how to do computational fluid dynamics type simulations, it will help you by taking away the coding and the scripting that you would need to do with OpenFOAM, and it helps you just focus on the decisions that you need to make and seeing how those decisions translate to differences in the results. So it helps, but you need to be somewhat familiar with the concepts and with the theory. Now, what are the steps? First, you need to define the geometry of the building that you're looking at. Then you need to generate a mesh for that and the domain. You need to set up boundary conditions, how the wind is entering that space. You need to set up the numerical solver and the turbulence model, and then decide which points are you going to monitor throughout the analysis. In the end, you get the wind, the flow field And also, as I mentioned earlier, VUQ connects this immediately to a structural analysis. So once you have the wind available, you can also get structural behavior available in terms of drifts or accelerations in the structure, which is pretty powerful. So how does this look like in the user interface? Because I can show you a really nice slide, but I also want to show you how this actually looks like when you are running an example. So I'm showing you how this looks like when we run example 6, where we are looking at the Willis Tower in Chicago as an example, and we are simulating the wind flow around it. You can do this by downloading VUQ today, and the example is available right there. You can load that example and run this problem. So it's available to all of you. This first slide or first screenshot shows how our applications are structured. What we do here is on the left, this is all of our desktop applications. We have the workflow, each step of the workflow available, and you can see that we walk through general information, simulation model, event information. This is the wind field or wind generation. Then finite element modeling, engineering demand parameters, what kind of information you need about the building, and random variables and results. So that's the general layout of every desktop application we have. And what I'm going to focus on is the event part. So first, we can use a single multi-degree of freedom stick model for the building for the sake of simplicity. In this example, it's 108 stories, so it's 108 masses in that multi-degree of freedom model. And then in the event part, we have multiple options, but in this case, in this example, I'm showing you the CFD option, just to give you a flavor of how this looks like. When you are running a CFD simulation, you can see that we have a number of tabs here that walk you through the exact same steps that I showed you in the slide before. And I'm not going to go into the details here because we don't have time for that in this presentation. But if you are interested, again, we have detailed documentation. And if you still have questions, we have the office hours where you can connect with us and we will help you understand how the tool works. So after starting, you can load the geometry. It looks like this. You can see that there's a bunch of settings available to fine-tune what you do here. Then meshing is probably the most involved part of this, where you have to make quite a lot of decisions. So after setting up a background mesh, you have to do a number of steps to refine that mesh. Just to give you an idea, we provide you ways to do surface refinements, edge refinements, and so on. And in the end, you are able to generate something like this within the tool. So it's semi-automated. You have to make those decisions, but the generation is done automatically in the background by connecting to the appropriate tools that take care of this. Then boundary conditions is next, where you set up how the wind enters this space and leaves this space. Again, you have a number of choices here, including our turbulent inflow tool, which is also a tool that is developed by the SimCenter, and it allows you a way to set up complex boundary conditions for these analyses. The numerical setup, as I mentioned, is about picking the solver and making decisions about how to model turbulence. And then you can decide which points to monitor throughout the analysis. So as you see, we are following the same steps that I mentioned in the previous slide, and you can see the level of complexity of this setup in the tool if you are going through it yourself later, today or whenever you decide to try it. After setting up such a workflow, this is also a very important detail, you can run these analyses on the Texas Advanced Computing Center thanks to DesignSafe and thanks to NSF. So the National Science Foundation provides you access to that computing center, and DesignSafe makes it easy to access it. And we are collaborating with them so that you can use a click of a button and then send your model there. The analysis is done there, and you can get the results back into VUQ on your computer automatically. This is making it very easy and cheap, free, to run computational fluid dynamics analysis and to experiment with these things as a student or as a researcher who's just getting used to how to run these things. All right, so you can run these on DesignSafe, and then when you get the results, VUQ provides you an overview of what happens to the building behavior, or the wind speeds. It doesn't give you every detail because we believe that researchers will have many different kinds of questions and post-processing needs. So what we do is we give you access to the raw data and allow you to do your own post-processing afterward. One thing you can do, for example, is you can access the full simulation data on DesignSafe and use ParaView to look at the wind flow and use that to confirm if the analysis is doing what you wanted it to do. We did a number of validations. So you can see the Willis building right here at the bottom left. We also looked at simple shapes. We looked at low-rise structures. We looked at empty domain simulations, and we compared the simulated results with what was measured at the experiments. Professor Gorley was a part of this effort, and we did this so that we can be sure that whatever we provide you as a tool is giving reasonable estimates if you set up the analysis properly. And you can see that throughout these examples, we got good results that we found satisfactory. So you can trust that if you know what you're doing, then the tool is going to work as expected. Now, if you want to move beyond a single building analysis, we also provide you a couple of options. You can look at a neighborhood scale simulation where you can generate buildings around the building of interest, and you can consider how they affect the wind flow and the wind loads on your building of interest. So that's one thing you can do, but an even more exciting recent feature that was developed with collaboration with Professor Spence is using our Braille's tool, which is Braille's++. It's an inventory generation tool. You can pick any region of interest, get the footprints and the building heights from that area, and you can create your domain, including all of those buildings automatically. You can do the usual steps that I mentioned earlier, like creating a mesh and all of those, and run a CFD simulation for this domain and consider the actual buildings around your building of interest and how they affect the pressures and the wind speeds in that area. This is very promising. It's also quite expensive to do these simulations, as you can imagine. I encourage you to try it. I encourage you to talk to Professor Spence. He's right here if you have any questions. And let us know if you have any suggestions on how to improve these features or make them even more engaging and useful for your research. So this was the CFD part. There's also another area that I wanted to highlight, which is probabilistic assessments using stochastic loading. In this case, you are using experimental data that either measured wind speeds or pressures or forces. We have these three covered in three different methods. And this is from Professor Spence's group and his co-authors and students. And we are able to create a stochastic loading based on the experimental result that you provide so that you can generate multiple realizations of the loading that represents the same kind of wind time history. This is very powerful when you want to do probabilistic analysis and only have a handful or only one result that you could work with otherwise. So again, this is a nice way to illustrate how experimental data and computational methods can be complementary and can support each other. Finally, I want to spend a minute on performance-based wind engineering. We can generate complex wind loads and then couple them with complex structural models. It doesn't have to be a stick model. You can bring your own OpenSeas model that could have various kinds of nonlinearities, and you can do a proper nonlinear dynamic analysis on that. And besides looking at what the structure does under wind, how it moves or what kind of accelerations happen, you can also take a step further. And this is also available in VUQ, and identify areas on the structure that you will be interested in looking at for damage assessment. So in this example, this is also one of the examples that is available in VUQ. We are looking at a low-rise structure, and we are identifying parts of the roof and the windows. And when we do the CFD analysis, we are collecting pressures for those areas. Then VUQ can export these pressures in a file that can be used by another tool that we develop at SimCenter. It's called PBE, that's performance-based engineering. You can import those pressures into PBE and run a damage simulation, considering fragility curves that are specific to those components that you identified. So windows, for example, or roof tiles or other important parts of the structure. So this allows you to do a high fidelity damage assessment of a certain structure and get good information on how each component gets damaged in a probabilistic simulation. The fragilities that are used in this type of analysis are also collected and shared by the SimCenter by looking at what is available in the literature. So we worked with Rachel Hamburger from the University of Notre Dame. She's a graduate student there, and Tracy Kijewski-Correa, her advisor. And we collected a large number of fragility functions that are available to you and are available in PBE automatically, and you can use them to do these types of damage assessments with the help of VUQ and the CFD analysis there. So I would like to close this with a vision on how this connects to regional analysis. I've been talking about local type of analysis, single building or single building with its surroundings, where we aim to understand what happens to a building. What we would like is to see how this translates into getting higher fidelity information about the buildings when we do a regional hurricane risk assessment. And the way we see this happening is through multi-fidelity simulations, where each building can be simulated using one of a number of methods. You can choose the method that is appropriate for your building. If you are looking at the Willis Tower, you will probably want to do a high fidelity specific detailed simulation. But if you are looking at low-rise structures, you might be okay with a surrogate model that is calibrated to the high fidelity simulations, but you don't need to bring those specific CFD analysis into the regional risk assessment. So we see this as an opportunity to connect the local scale detailed analysis to a regional scale risk assessment. And we can do this with R2D, our tool for regional risk simulation, which connects everything from hazards to recovery. It's multi-hazard, it supports multiple types of assets. You can bring multiple types of fidelity into this tool. Again, check it out if you are interested. And if you run these in R2D, what we hope is that there will be a feedback loop for experimentalists, for computational simulation experts, which tells them what are the needs in regional risk assessment that need to be served by improving the methods for local analysis. And with that, I will stop here to give time for everybody else. I encourage you to check out our website. We have documentation, we have other webinars available, and we have office hours where you can connect with us and you can ask us questions if you would like to get engaged with our tools. And with that, thank you very much.
Okay, thank you very much, Adam. That's a really nice overview of what we have with VUQ. Out of the interest of time, I would like to now move on to the next presentation. This will be by Professor Goulet, who is going to give us an overview of the educational module that is actually accompanies VUQ. So, Catherine, the floor is yours.
Catherine, you're muted.
Okay. I'll go a little faster because I think we want to leave time for questions and discussion at the end, right?
Great. Yes, thank you.
So this is just a brief overview then of the educational model that we've developed, focusing really on the use of large eddy simulations for wind loading prediction. So it really ties into everything that Adam just showed you to teach people how to do these simulations correctly and what's important. I have the overview here. So in total, the educational model has 5 slide decks, and then it has tutorials and assignments as well attached to it. I'm going to walk you through the first one because it really discusses the introduction, the learning goals, and the outline of the module. Then I briefly want to discuss synergy between this educational model and an ASC pre-standard on computational wind engineering that is currently being prepared and that should be published, if all goes well, in the summer of 2026. And then last is where to find this material. Okay, so this is the first slide deck. It acknowledges everyone who has contributed to this. So again, Abi really did a lot of work on the tutorials and the assignments that are essential to the module. And then the lower row is students of me that have contributed to the module and the results that we're showing. So this first introduction covers the motivation, why is this important, then steps in setting up a model, the learning goals and the module overview, and then a brief intro to the tutorials and the assignments. I'm going to skip the motivation out of interest of time, because I think if you're here, you care about this problem already, right? So we're just kind of making the case for why CFD can be a good addition to traditional building codes and standards and wind tunnel tests for getting wind loads. Showing some initial flow visualizations to indicate how velocity fields relate to pressure fields, which is really one of the strengths of CFD, right? That you get that simultaneous set of information to do flow analysis. We can also do simulations that cover much bigger areas than what we would typically do in a wind tunnel. There's lots of opportunities to explore non-stationary wind effects. We're not discussing those in the module, but it's worthwhile highlighting that. And then, of course, yeah, lots of other things that could be thought of. So this is the important part. Now, what are the steps in setting up a computational model and that can affect your solution? So really, the first thing is to decide what is it that you want to predict and what is the system of interest. So what are your quantities of interest? And this refers back to some of the things that Adam was saying. The question here is, are you looking at overall base forces, moments, for example, or do you want very detailed cladding loads on the structure? That is going to determine how fine your grid resolution has to be, for example. Then the physical processes and the relative importance, since we're focused on wind loads, these are kind of consistent, right, across all the simulations that will run, but it's important to create that understanding so that people know what is important in the simulation setup. And then the geometrical characterization, the modeling of the buildings and the surroundings. Once you have done that, you need to turn that into a mathematical model, right? So that's your governing equations. We're going to solve the filtered Navier-Stokes equations here. So we're doing large eddy simulations. That requires some phenomenological modeling. We need a subgrid turbulence model. We're most likely going to need a WAL model as well. And we need to define boundary conditions. Then in the third step, you need to discretize that continuous set of equations, right? Your partial differential equations into a discrete representation. So you have to create a computational grid, you have to discretize your equation, and you have to solve that discretized system. And then last, you're going to analyze your results and do quality assurance. And throughout this process, right, there's a number of simplifications and assumptions that you're making that can affect the predictive accuracy. And the goal of this module is really to provide background on all of these and to identify the steps that are really key in ensuring that you get good predictions at the end. So the learning goals are that after completing the model, your students will be able to list the model choices that affect the results of a wind loading analysis using large eddy simulations. They can use the knowledge to assess the quality of an LES prediction of wind loading. And they can run and post-process an LES calculation for wind loss assessment using VUQ as well, using the tutorials. So the overview of the module really follows those 4 steps. So in the first slide deck after this one, so in the second slide deck, we talk a lot about the wind loading flow physics, the quantities of interest for wind loading analysis, and then how to characterize the geometry. In the second slide deck, we cover the governing equations. We talk about subgrid turbulence modeling and about WAL modeling, and then about the boundary conditions. So inlet, outlet, sides, top, etc. In the third one, or the fourth slide deck, we go from the governing equations to the numerical solution. So we illustrate the importance of the numerical schemes using a very simple example of what a truncation error is. We show the effect of grid resolution on the results, and then we discuss the solution step and what is important to look at when you use iterative solution methods. And then lastly, the last slide deck looks at the calculation of statistics based on the simulation data. And it talks, maybe most importantly, of everything here about verification, validation, and then quality assurance of your results. And the key point here is really in these first two steps, we're going to emphasize the importance of using a two-step simulation process, where in the first step, you're going to make sure that you correctly model the wind. So you do a simulation without a building. It's just an empty wind tunnel case, if you want to call it that. And you make sure that the wind characteristics that you get at the location where you want to put your building next are okay. And then next you add the building and you make sure that you have enough resolution. And when you do these two things, you can really make sure that you get quality assured simulation results. So that's the emphasis throughout. The tutorial follows those two steps. So the first tutorial is going to show you how to model an atmospheric boundary layer flow using large eddy simulations. And in the second tutorial, you're adding the building into that domain and you learn how to obtain forces and wind pressures. And then the assignment focuses on grid sensitivity to really reinforce that importance of grid resolution in wind loading calculations. This is just at the end of each of these little sections. I have a little quiz that you can just ask the students right after teaching it to kind of test if they retain the key concepts. Okay, the synergy with the ASCE pre-standard. So first I want to acknowledge that that's definitely not just me. There's a lot of people that have worked on this for quite a long time now and put in a lot of effort. We have people from industry, from some of the main wind engineering companies, CPP, RWDI, there's Thornton Tomasetti, Ramble, Arup represented. And then we have people from industry as well. SOM is here too. We have a peer review team that has been looking through different drafts that we've generated and has been giving feedback. So what does that standard look like? So we have two chapters that are more introduction, general computational wind engineering. But then the main meat of this document is really all things that are being touched on in the educational model. So chapter 3 talks about wind climate and characterization of wind flow conditions. We touch on that very briefly in the second slide deck. Then we have general simulation requirements, wind flow simulation, and building aerodynamic simulation. And these are really the key components of how do you do these LES simulations? What do you need to do to make sure that your results are going to be accurate? And importantly, this really outlines that two-step simulation process that we are emphasizing in the educational module as well. So the standard is going to require that you do these two steps in the simulation process and make sure that you demonstrate through acceptance criteria that first you're modeling the wind accurately, and that second you have enough resolution to resolve the turbulent structures that are important around the building. Yeah. Then we have calculation of design wind loads. We really only touch on that very, very briefly in the educational module, but we'll provide resources if people want to learn more. And then we do talk about quality assurance. So right now, there's no direct connection between the two because the slides for the educational module were done before these documents really started to take shape. But there will be new releases and updates to the educational module that will explicitly reference the pre-standard as well. So accessing the material, so you go to the SimCenter website and then under Knowledge Hub, you go to Teaching Gallery and then you see a list here of different teaching resources that are available. If you scroll all the way to the bottom of that list, you find the Computational Wind Engineering Educational Model. And when you click on that, you'll get a drop down. And when you scroll down, you get links to all the material for the modules. So for the tutorials, you see PDF files, simulation files, videos. They link directly to all of that, as well as the homework assignments. For the lecture slides, I have a setup that allows me to update things quite easily. So if you click on the lecture size links, you will go to my lab's GitHub page for this LES educational module. There is a README file there. If you want to download it, you go to the latest release and you download the files there. So if you click on the latest release, you will see all of the files available there for download. Right now, there's both the PowerPoint files, and you're welcome to modify, right? There's PDF files available, and then before the winter break, there will be videos added with recordings as well. So you can choose whether you teach it yourself or if your students watch the recordings. And that's all that I had. I hope I didn't go too long. Yeah.
Perfect. Thank you very much, Catherine. I'd also like to just mention to all the participants here that Matt did put into the chat a link to the educational modules, including this one and others. So if you're interested in checking that out, as I said, the link is in the chat as of now. All right, so for our next portion, what I'd like to do is invite David. He's going to give a perspective on both incorporating the educational module into curricula, as well as experiences using SimCenter tools in research workflows. So David, the floor is yours.
Awesome. Thanks, Seymour, for the opportunity here. So I don't have slides because I'm going to keep this pretty short in my discussion, but I'm going to follow on with Dr. Gorley's presentation and just give an overview of how that actually worked out in our course. So Dr. Gorley was kind enough to take her spring break, I think it was, and wake up at 8 a.m. or not wake up, be ready to teach at 8 a.m. and guest lecture for our spring 2025 wind engineering class. So that worked out fantastic, and I really appreciated her and Dr. Rabi as well and being willing to do that. So the class itself it's a dual-listed sort of graduate and undergraduate class. There were 13 graduate students, 5 undergraduate, and this is within a typical civil environmental engineering department curriculum. There's only one PhD student. So most of these were master students that are, hoping to graduate and go on and join typical, consulting engineering firms. So this education module came in about 2/3 of the way through the course. So they already had some background on ASE 7 and sort of fundamentals of turbulence and things like that. And so this education module came in kind of a perfect time to reinforce some of those concepts and then build on it with adding in the CFD focus. So it went really well. The reactions I got were overwhelmingly positive on it. I even had a couple of the students, one of my graduate students, who mostly does mass timber work with me, and mentioned that he wished he knew about that earlier. He would have liked to have gone and done his master's thesis on CFD and stuff as well. Like he was really engaged in it. So that all went well. So it was structured as obviously the 3 50-minute lectures for that week. And then we had the accompanying assignment that the students all went through. So they all downloaded WeEQ, they set up OpenFOAM, they connected with DesignSafe and TAC to run the simulations. They did all of that themselves and went through that process with the help, the excellent support from Dr. Tim Cockrell as well at DesignSafe. So there were probably the biggest hurdle in that was just the setup. Again, with the background, these are typical kind of CE students. We have a very traditional curriculum here that we've tried to improve that over the last couple of years, but this class did not have a lot of strong coding background or anything like that. So this was all pretty new to them. And for the most part, they were all able to get it going. Probably the biggest issue was, again, just in installing OpenFOAM correctly. If you made a small mistake there in that process, it was very easy to get off track and then try to figure out how to uninstall and reinstall the right way and so on. But once we got through those, the process was very smooth. I think we had a couple instances where maybe one of the jobs that were submitted timed out or had an issue like that. But most of the students were able to finish and process the data, complete the assignment, and seem to learn a lot from that. So what I think was really cool about just this education module, again, for what were just typical kind of undergraduate, master's level, civil environmental engineering students, was it really lowered the bar for them being able to understand CFD and feel confident that they could at least do a basic simulation themselves. I think in some ways, CFD and AI, for example, can very easily become these like black boxes that, okay, it's just so complicated that there's such a high learning curve that, a typical, CE student may just stay away from it entirely. And I think, this tool and some of the others sort of lower that bar while still giving them an appreciation that, this is not just you dump your stuff in and magically you get a right answer out. We want to avoid that. but it gives them a benchmark that, hey, we can start here. We're confident that we can get it working. We can analyze the results, and now we can branch off from here with the tools and the knowledge that we've gained. So again, it was a very positive experience, and certainly appreciated again Dr. Corley, Dr. Abi, and the whole Design Safe team for supporting that and letting us trial that this spring semester. So in terms of what we've done since then, we had one team of students that actually used the output from the WEEQ simulation as their final project for the class. They did some dynamic analysis based on the pressures and then compared to ASE 7 kind of gust effect factor provisions. So that was interesting. And then I have one PhD student who's still working with it now, basically running simulations for wind loads on irregularly shaped buildings. We have a couple of really nice data sets back from my days at the University of Florida, where we had field data from the FCMP program. We have field data on a couple of houses. And then we also have 2 or 3 different wind tunnel companies or labs that simulated the pressures in experimental wind tunnels. And then we're also now doing the CFD simulations on those as well. And we're hopefully presenting that at the upcoming 2026 Computational Wind Engineering Conference. So that's been good. Still working through the program or using WEEQ for that process. So again, I'm happy to answer any other questions if you have it on the modules or learning curve or anything else. But it was a great experience, and very appreciative of the tools and effort and time that all went into that.
Perfect. So thank you very much, David. That brings us to the last portion of this research engagement meeting.